keynote speaker in this session. I lead the LAM distinguished chair at UC Berkeley, and he will give, he's a pioneer of wearable biosensors. Actually, I started working on biosensor while I was a postdoc in Ali's group. So welcome, Professor Javey, for the talk on the wearable sweat sensors.
All right, thank you very much, Wei. Thank you also for inviting me to give this talk today. So I will try to use the next 20 minutes or so telling you a little bit about the work that we are doing at Berkeley on wearable sweat sensors. And the big vision really is to move towards big data for human health, as you will see. Now, let me start by giving you a bit of a motivation as to why we're interested in sweat. First of all, it's very easy to access sweat. We all, of course, are very familiar with that. And under extreme conditions, athletes can lose up to 14 liters of sweat a day. I mean, that's just a tremendous amount of sweating that you can undergo through. Sweat has a number of biomarkers in it, and they have been investigated in the past using off-body measurement techniques for a variety of applications. And in fact, the first mention of using sweat analysis in the context of, in the medical context, goes back to 1606. And this is well before modern medicine. There was a myth that salty babies, the babies with salty skins, die young. And today it's believed that the reference was to cystic fibrosis. And in fact, for detecting cystic fibrosis, the gold standard today is to do sweat analysis. Now, what we want to do is to develop wearable sweat biosensors. And we want to use this as a platform to be able to do continuous monitoring of different biomarkers in the body, non-invasive and continuous. That's really the key. Today, the existing methods lack that ability to a large degree. When we do blood tests, that's not continuous. We do discrete measurements over time, and you often do blood tests only when something is wrong. And by being able to monitor subjects, individuals over time, looking at their dynamic changes, formulating baselines, we believe that we can really change the way healthcare is done today. Now, there are two different applications that we envision for these devices. One is for athletic or fitness tracking. And there you're dealing with subjects that are sweating quite a bit. So you're monitoring the subject as they undergo extreme exercise events. The other application is for diagnostics and health monitoring. And there you're often dealing with subjects that cannot move or they cannot exercise as much. So the two platforms require very different device designs and device considerations, which I will talk about. In one case, you're dealing with large volumes of sweat, very large sweat rates. In the other case, you're dealing with very small sample volumes, very low sweat rates. Again, the key is to be able to then collect big data and formulate individualized baselines. Now, as we started looking at this problem several years ago, we started to run into a number of challenges. And so over the years, we constantly try to solve some problems and we identify new ones. And this is just a short list of some of the problems that we have faced over the years. And first of all, we're dealing with often very low sweat rates, very small sample volumes. And we're dealing with typically low analyte concentrations. And in analytical chemistry, we teach students that if you have very small sample volumes and low concentrations, you're in trouble. And in this case, we are dealing with both. We have to mitigate evaporation if we want to sample evaporation, water evaporation, if we want to really get the true concentrations correctly. We have to deal with contaminants on the skin. This is something that we started looking at a few years ago for the case of glucose, when we were doing glucose sweat sensing, many of the hydrating soaps that you buy, they have sugars added in them. And so if the subject had used those hydrating soaps with sugar in them prior to the experiments, then the question, of course, is what is that sugar or glucose content that you're reading? Is it from sweat or is it from contaminants on the skin? Then, of course, you need to have reliable, reproducible sensors with minimal drift. And then you need to start to move to collecting big data sets and start formulating correlations and decoding sweat composition. So we started this project several years ago, and in fact, we started this when Wei Gao was a postdoc in my lab, and since then we have looked at developing a fully integrated device that can do selective monitoring of a large array of different biomarkers. We have shown you can do metabolite sensing like glucose, lactate, different ions. Heavy metals, that's really an interesting one. When you're exposed to heavy metals, the body tries to get rid of them almost immediately through urination and sweating. So, the sweat analysis of heavy metals really tells you right away if you're exposed to heavy metals well before you're poisoned. Drugs, many drugs do show up in sweat, and in some cases it's pretty well known that there's a strong correlation with blood. Vitamins, we have looked at, for example, vitamin C, and there is a strong correlation. Skin temperature, sweat rate. And the device that we have, this is just one example prototype. This is the first prototype that we made when, in fact, Wei was in my lab. This prototype has two components. There is the disposable part. That's the part that is shown in white here. That's the part that comes in contact with sweat. That's the part that comes in contact with the skin. That's where the transducers are. That's where your sensing elements are. And that's then interfaced with an electronic board. And the electronic board signal conditioning, processing, and data transmission. And in this case, we use 11 off-the-shelf chips, but of course you can design a single chip that does all of it, and you can design a single ASIC. And in fact, we have worked with IC faculty, and we have now single chip ASICs that can do all of the functionality of this board on a single chip. It's nothing fundamental there. And you can do multiplex sensing. You can put different transducers there. You can imagine you can start to really measure an array of biomarkers, or if you want, you can just measure a single biomarker, up to you and up to what application you want to target. Now, we have over the years looked at packaging and different form factors. This is a work that we did a couple of years ago, where we basically made a smart watch, and with a display and with the integrated sweat sensors. And in this case, the smartwatch was self-powered. The band in this case has a very cheap photovoltaic cell. It's just an amorphous silicon cell that harvests the ambient lighting, and you can put a battery there, and you charge the battery with that ambient lighting. These devices do not use much power, so just a very simple photovoltaic cell, similar to the ones that are used in calculators, would do the job. And this is just one form factor. You can also make form factors in the form of a Band-Aid or a patch, depending on what application you're targeting. So this is one example set of data from early on, and this is really kind of to give you an idea of the type of data that you can start to collect. You can get a subject. In this case, we got a subject to bike for us, and we modulated the biking power. That's the top panel, and we measured different vital signs and for example, heart rate, VO2, VE, using traditional sensors. And at the same time, we measured using our sensors skin temperature, lactate, glucose, sodium, potassium, and so you can really imagine the type of data that you can obtain, and you can obtain really a large data sets from just one short experiment. In this case, it's just a biking experiment. Now, early on, the very first device that we showed was working fine for athletic applications where the subjects sweat quite a bit. But the question, of course, was, can we develop devices that can be used for medical applications where you cannot get the subject to bike for you? And one platform that we explored soon after our first work was to use iontophorosis. And iontophorosis is a FDA-approved process used by clinicians today. And the concept is very simple. You have a hydrogel. It's loaded by a drug, FDA-approved. They even use it on infants. You pass current through this hydrogel, and the drugs go under the skin. They locally activate the sweat glands, and you get local sweating. And today what they do in clinics is that they collect that sweat, they send it to an analytical lab, and to analyze typically the sodium and chloride ion concentrations. So we borrow the same concept, except that we have also integrated sensors using the same patch. So the same patch not only induces iontophorosis, but it on body, it analyzes the sweat that is induced as well. And so this is one way that you can design devices for clinical applications. Now, the problem with iontophorosis is that the sweat rate here is sensitive to the specific drug that you use, to the specific iontophorosis conditions. And what we have seen is that if you do iontophorosis too many times on a single subject, their sweating profile does change. Specifically, their sweat rate profile changes. We don't know about composition, but the sweat rate changes. So it's probably not an ideal platform if you want to do continuous monitoring. You just don't want to do too many iontophorosis on a single subject over time. So we looked at this problem and to see if we can somehow design a patch that can measure thermoregulatory sweat and sweating events without any induction, without any drug, without any heat, without any physical stress, exercise. And of course, we're always sweating. And we often don't notice it because the sweat rates are very low and evaporation happens very quickly, but we are always sweating. When we're sitting, when we're sleeping, we're always sweating at different sweat rates. And so here, what we did was we designed a device that has a microfluidic, and this microfluidic, the dimensions were optimized. We made the dimensions as small as possible, the cross-sectional areas as small as possible, while it's still allowing for the fluid to go through it. So the resistance has to be, it's a compromise between the fluid resistance and the volume of the chamber. And we design a collection well as well properly that can allow for collection of very small sample volumes, very small sweat rates, and would enable us to measure the sweat rate of the subjects being at rest or near rest, and at the same time analyze the composition of that sweat. And I really genuinely believe this is a game changer, and the solution ended up being very simple, and I will not talk about the detail, but again, the collection area had to be optimized, and there are different components within the collection area, and the microfluidic dimensions also had to be properly designed and to enable for analyzing very small sample volumes and very small sample rates. So you can look at the details in the paper, but I really believe that this is going to change the application of sweat sensing. We can now do dynamic sweat rate monitoring when the body is at near rest. These are just some results. In this case, we are just showing the optical images of the microfluidic as the sweat goes into the microfluidic while the subject is at near rest. We put these patches on different parts of the body, and the shoulder, upper arm, abdomen, thigh, chest, and so on and so forth. In this case, we placed them on 8 different spots. And We use dye here, coloring dye, just so that you can visualize very readily the movement of sweat in the channel. And just from this movement of sweat in the channel, you can get the sweat rate, and you can clearly see that for the subject being at near rest, we could measure sweat rate at all locations that we explored, and we also found that the fingertip and the thigh have the highest sweat rates, which is consistent with literature. Now here, the measurement is done optically. You can put electrodes in there. In fact, we have done that. And by putting electrodes through the channel, you can electrically read out where the liquid front is in the channel. You can electrically read out the sweat rate. Now, to do larger scale subject studies, really it's important to be able to produce sensors reliably, large number of them with very small sample to sample variations. And for that, we have formed a very fruitful collaboration with our colleagues at VTT. And they have amazing roll-to-roll processing capabilities. And here what you're looking at is a sheet of microfluidic based sensors, sweat sensors that are roll-to-roll printed. And we get these sheets that are in some cases 100 meters long. And then all we have to do is basically cut them out. And in this case, the marked areas, each marked area is one sensor. This is the disposable component that gets interfaced with the silicon electronics component. Now, let me show you some example applications that we have explored over the years. Early on, we work with Cystic Fibrosis Center at Stanford. I mentioned to you that for cystic fibrosis detection, gold standard has been for the past few decades sweat analysis. And as a rule of thumb, if the sweat chloride concentration is less than 40 millimolar, CF, cystic fibrosis, is very unlikely. And if the concentration is more than 60 millimolar, then CF is likely to be diagnosed. And today, genetic testing is so cheap that at this stage you order genetic testing. So we went to Cystic Fibrosis Center at Stanford, and we installed these devices on patients. And we also, of course, looked at healthy subjects. And we could clearly see that in the case of healthy subjects, we looked at multiple, the chloride concentration was well below 40 millimolar. And patients, again, we looked at multiple patients. Clearly, the chloride concentration was, in this case, well above that 40 millimolar, with the average being closer to 90 millimolar. So this was a sanity check, really proving that our devices work, and they work well for a very well-established application. Another case study that we have looked at is for athletic applications. You want to know if a athlete is losing sweat, is losing fluid by sweating. You want to monitor that, and you want to know how much they have lost, how much bodily fluids they have lost. And that provides very important information by itself. If a subject is exercising at the same level and all of a sudden the sweat rate drops dramatically, you have to start worrying about the subject. It's an early sign of dehydration. If the subject has lost too much bodily fluid by sweating, that's also concerning. And one definition of dehydration is 2% body weight loss by sweating. And so what we have shown is that by installing these sweat rate sensors on the body and measuring local sweat rates, at least for the same individual, we can predict the whole body fluid loss as they undergo exercise. So this can, in fact, in principle, provide us with very valuable information when the subjects are exercising. Another case study, this is from our newest patches where we don't induce sweating. This is just a thermoregulatory sweat at near rest. We installed a patch on a subject and we monitor them for 24 hours continuously. And in this case, I'm just showing simply the sweat rate, but of course, you can also do analyte concentration measurements at the same time. And in this case, we monitor the ambient temperature. And so the top panel is showing the ambient temperature for the subject, the place that the subject was located. And we measured their heart rate during these 24 hours. The subject was sitting around, was eating, walking, sleeping, and also having a Zoom talk. And you can see the fluctuation in heart rate. It's clearly there, but it's not very large. If you look at the sweat rate, on the other hand, what's really astonishing is that during the Zoom talk, this subject, their sweat rate dramatically shot up by almost 2 orders of magnitude, and this is simply from stress. And of course, we all know this, that you sweat quite more when you're under stress, and in this case, we were clearly able to monitor that. And we also install a sensor on a student taking an exam, and this is a Zoom exam last year. And we monitor the sweat rate before the exam, during the exam, and after the exam. And again, the same thing, that sweat rate was low and towards a magnitude increase in the sweat rate when the exam started. And it amazingly took half an hour after the exam was over before the sweat rate decayed back to the baseline value. So you can really get meaningful information about your stress levels by looking at sweat rate by itself. Another interesting case study was we looked at a diabetic subject, and it's pretty well known that for when your glucose level, the blood glucose level is too high, the sweat rate becomes very, very low. And similarly, when the blood glucose levels are way too low, the sweat rate just shoots up dramatically. And in this case, we monitored the interstitial fluid glucose levels, basically the blood glucose level, and we monitored the sweat rate. And you can clearly see that that when the glucose level was very high, the sweat rate was very low, and as the glucose levels went down, the sweat rate shot up. The whole time the subject was just sitting, so there was no change in physical activity. This is again another interesting example of how sweat rate by itself can be used. Another application that I believe there is a lot of room for exploration is for drug analysis, and specifically for personalized medication. This is one application case that from very early on we identified to be important. And we all have very different metabolism rates, very different absorption rates for drugs, and that those values change over time from day to day, depending on what we eat, how much exercise we undergo through. There are many drugs where the dose has to be fine-tuned for the subject to operate well, especially the drugs that affect the function of the brain. And today there is really no good way to prescribe the dose. They basically just give you a certain dose, and they just try to see how well you operate, maximize the number of hours that you can operate well, and then they tune that just based on your response. But by being able to monitor the drug levels in the body over time, you really can start to think about personalized medication and personalizing the dose of the subjects. And so for that, as a proof of concept, we looked at the easiest drug that we could access, which is caffeine. And in the case of caffeine, sweat caffeine and urine caffeine and blood caffeine are very well known to be correlated. And so this is an older work, and in this case, we have to get the subjects to bike for us in order to be able to access their sweat. And so the subject took caffeine at time 0, and then they started biking, and we monitored the sweat caffeine level. And you can clearly see that over time, the sweat caffeine level rises. There's a peak at about 60 minutes, and then there's a decay. And so from this, you can extract the absorption rate and the metabolism rate of caffeine. And it turns out that the optimal time is about 60 minutes. So if you want to give a talk, the key message here is to take your coffee 60 minutes before your talk. And indeed, in literature, that's roughly what people see as well. Another interesting drug is Ldopa, levodopa, and that's a drug that is used for Parkinson's disease. Again, the dose control of it is really essential. So we developed sensors to measure Ldopa concentrations in sweat. And again, we were able to show that we can measure the absorption rate, the metabolism rates, and for this particular drug by just simply doing sweat analysis. So with that, I'm going to come to the conclusion. I hope I was able to give you an overview of where we are and what I think are some of the interesting challenges or opportunities, I should say. And really what we want to be able to do is to be able to decode sweat, figure out what sweat can tell us, figure out where are the correlations, what analytes give us strong correlations or weak correlations, and be able to do medium to large scale populations. And I think as a whole, the community has made tremendous progress over the last few years. And there has been a lot of advancements in this field. So with that, I will take any comments or questions that you might have, and I will just leave the acknowledgement slide up, acknowledging all the various students and postdocs over the years that have contributed to this project. Thank you very much.
Thank you very much, Ali, for the wonderful talk. We have some time for questions. I saw already 2 questions in the chat I can read. So thanks for the great talk. You said only the sweat sensor is of single use, and the rest of systems such as electronics is being reused. Is there any other reason for electronics not being single use than simply cost? Is there any contamination concerns sharing the electronics of the wearable sensor across babies in case of cystic fibrosis example?
Yeah, I mean, in the case of something like a cystic fibrosis or medical application, you can imagine that the electronics part, perhaps you would not want to share between the different subjects if there's a concern. And so there you could imagine that you would use the electronics also once. The electronics are not going to be that expensive. And to design an ASIC and the cost of an ASIC is to manufacture, to calibrate, and all that and package is going to be about $1 per chip. That's the standard cost for an ASIC. But then of course there is the R&D cost that goes into it. For medical application, that's really nothing. If you think about the cost being even $10 or tens of dollars at most, that's not an issue. I think for consumer applications, it just makes sense that the subject reuses that. And today, there are commercial FDA-approved interstitial fluid sensors that go in by a little bit. They're used for glucose sensing, continuous glucose sensing diabetic patients. They work very well. The electronics part is reusable there, and for the same subject, of course. And they last a long time. Eventually they will fail and you just buy a new one. But the sensor part is you just use it once, and they last for about a week or so. So you're supposed to change them once a week. So that's how we envision the devices working in the future as well.
Great. We have another question. Very interesting talk. How are the sensing material fabricated? Can you tell about their stability under multiple measurement, bending, mechanical strengths?
Yeah, very good question. So the fabrication is, we have different fabrication schemes. We, over the years, for example, use lithography-based processes and also printing-based processes, including roll-to-roll printing. And most of the work that I presented, except for the earlier ones, are based on printed devices. So everything is printed. The microfluidics are processed roll to roll, and the electrodes are roll to roll printed. In terms of the stability, that's really an area that we have focused a lot, and that's not the most elegant part, from the student's point of view. That you can't get science or nature papers by addressing stability, but we have had a lot of work on that over the years, just carefully trying to optimize the devices and really reducing drift. That's really the key, and we have put a lot of effort on that over the years. Now, in terms of bending, we work with substrates that are not stretchable, and that's done on purpose. We chose there are different schemes here. Some people work on stretchable patches that can conform to the skin. What we found is that is actually quite challenging to handle, because they're very sensitive to bending and mechanical movement and mechanical motion, and correcting for that is quite difficult, to be frank. And in some cases, you're looking at very small signals, and that really complicates things quite a bit. So we work with devices that are flexible, that can sit on the skin, but they don't stretch, they don't deform. So the amount of strain that devices undergo through is very, very small. And so you can